Done data set 4 with data set 3 because this is really quick, and the last one's the long one. So with this, we're just focusing on motive force and torque. So here's the back wheel of the car, there's the axle. I'm exaggerating the radius of the axle. Here's the front wheel of the car. Doesn't really mean anything here. This is just the frame of the car. So what's important is the rubber bands that are, or the string or whatever it is that's tied on right here. So this applies the band force. There's the center of rotation. This right here is the axle radius. The torque applied to something is the force applied at the edge of the thing multiplied by the radius. So if we had, like at the beginning of this unit, there was a picture of a wrench. And you apply a force here, R, we call the lever arm, and the torque is just the lever arm length times the force. So in this case, the force is the force of the bands, the radius is the axle radius. So for this first part, the torque equals RF, where R is the axle radius and F is the bands. And that's 0.052 for the radius and 37 newtons for the force. Now that 0.052 is greater than the metal, because as in this particular case, as they were winding this up, that made this thicker and thicker and thicker, so that increased the radius to be a little bit more than just the metal axle. So this is what generates the torque. And the torque gets exerted throughout the entire wheel. So there's, if you grab onto the wheel here or here or here at any point, you're going to feel the torque, the twisting force. So that torque is also going to exert a force over here. This is the one I've called the motive force. This is the force that the wheel pushes back with against the road. And it's also equal to the force that the road pushes forward with on the car. So the torque causes this force to happen, and it does it at this radius. So there's the same torque here as there is here. This radius times this force equals this radius times this force. But since this is a big radius and that's a small radius, this is going to be a small force and that's a big force. So let me write R wheel, F motive or road or whatever you want to call it. So you calculate the torque with the axle times the band force and you get this. And that gives you that. And then you set that equal to this and you plug in the radius of the wheel to get the motive force. So take this, plug it in for torque, set it equal to the radius of the wheel times F, and there's F. So this should be in newtons and that should be in newton meters. Now the last one. Yeah, so here's the basic formula. Just energy is conserved here. We're not including any energy loss. We're saying that when you wind up the car, all the energy that it has in the beginning gets transferred. That's just the assumption here. This is the stored motor energy from number 17. So 7.784 joules. When the car starts, there's no kinetic energy, and the potential energy at the end is 0 because it's used it all up, but at the end there is kinetic energy. So total energy in the beginning, 7.784 joules, equals 0 potential energy plus 1/2 mv squared. That's the kinetic energy that the car has because the whole thing's moving. This is KE translational. But it also has energy stored in the rolling wheels. The front wheels are rolling, so this is KE rotational for the front wheels. And then it also has energy that are stored in the drive wheels. So this is KE rotational drive wheels. And the formula for rotational kinetic energy is 1/2 I omega squared. So for the front wheels, we have to multiply 1/2 times the moment of inertia of the front wheels, which we have to go look up, times the angular velocity of the front wheels squared, plus 1/2 times the moment of inertia of the drive wheels times the angular velocity of the drive wheels squared. With regard to the angular velocity, I do a little substitution because what we're solving for is linear velocity. So angular velocity equals linear velocity divided by r. So wherever there is an omega, here and here, I substitute in a v over r. And since this omega is getting squared, I'm putting in v squared over r squared. Now the v's, this v, this v, this v, those are all the same v's. Those are the v's that are going this way. But for these different wheels, they have different radii. So when I'm doing the front wheel angular velocity, it's linear velocity divided by its radius. So this is the radius of the front wheel, and it needs to be squared. And this is the radius of the drive wheel, and it needs to be squared. So there's my big formula. What am I doing? I'm factoring out. Everything has a 1/2 v squared in it. So the 1/2 mv squared, if I factor out the 1/2 v squared, put it over here, v squared over 2, then this just becomes m. This becomes the moment of inertia of the front wheels over the radius of front wheels squared. This becomes moment of inertia of the drive wheels divided by the radius of the drive wheels squared. And what did I do here? I multiply both sides by 2 times this, and then I divided both sides by all this, and then I took the square root of both sides. So I did 3 steps here. So when I multiply both sides by 2, I get on the left side 2 times that. And when I divide both sides by all this, on the left side I get this over this. And then when I take the square root of both sides, I get this on the left side, well, formally on the left side. And then all that was left over here on the right was v, and then when I took the square root, I got v. So trust me that my steps were right here. So the last step is just to plug stuff in. This is the mass of the car. This is the moment of inertia of the front wheels, moment of inertia of the drive wheels, radius of the front wheels, radius of the drive wheels. And I had to look all that up. The front wheel moment of inertia is right. Oh, front wheel and axle moment of inertia is right here. I want that whole thing. And the rear wheel and axle moment of inertia is right there. That's the more important one. The mass is right here. The radius of the drive wheels is right there. And the radius of the front wheels is right here. So plug all that in and carefully calculate it all, and you should get this.